If you're a scientist or engineer, are you 100 years out of date? I'm a chemist, but I have worked with physicists, biologists, mechanical, electrical, and software engineers from many different industrial and academic groups around the world. Over many decades and many projects, I have learned that most scientists and engineers don't actually use the best experimental methods that have become available in the last 100 years. The purpose of this short video is to make those scientists and engineers aware of what they're missing and how they can become much more effective and respected in their professions. Let's get artificial intelligence out of the conversation right away. AI is about correlation, not causation. Correlation is often used by the general public to understand what's going on in the world. Science began in the same way, but developed into causation centuries ago. Here's an apparent correlation between ice cream sales and shark attacks at the beach. Since sharks probably don't like ice cream, it could be that summer weather is the real factor for both ice cream sales and shark attacks. Causation is found by experimental trials on likely variables that could have effect on results. Artificial intelligence is a good tool for looking at correlations in very large data sets, but not to understand the real causation. Our brains will never be obsolete. So how did science progress from philosophy to modern experimentation? The scientific method began as a gradual movement from a study of a divine order of the world and the heavens to the collection of data and mathematical models. Kepler and Copernicus calculated orbits based on the sun instead of the earth as Ptolemy did, but their numbers were not much different from Ptolemy's spheres. Galileo performed experiments with telescopes, balls, and ramps to understand the behavior of astronomical objects and falling weights. It was Newton that made measurements that produced predictive laws of motion and gravity. Ironically, Newton developed his mathematical methods while still believing in divine forces. Einstein then followed up with thought experiments that correctly predicted how light, space, and time interact. He found the right variables, and his measurements agreed with his models. During this same decade, a new methodology was developed that substantially improved the efficiency and quality of experimentation, which is the point of this presentation. Here's an example of the experimental work over decades to produce the gas law taught early in our science classes. We start in 1662 with Boyle's demonstrating that pressure and volume were inversely dependent variables. 118 years later, Charles finds a volume and temperature direct dependency. Then Gay-Lussac's direct pressure and temperature relationship was added in 1808. Avogadro proposed that atoms combined into molecules in 1811, although this was not accepted initially, but now we have the number of molecules and volume directly proportional. Finally, Clapeyron analytically put them all together in 1834. And we finally have the behavior of gases in a single model with 4 dependent variables and a gas constant R. Let's be clear about models. They are mathematical representations produced from validated experimental data that can be used to predict useful results. Here's the current standard model of particle physics. Many contributions over many years combined into 18 variables. So how do we learn to experiment today? Science and engineering subjects are taught in 2 parts. We get the answer first by learning the current theories as mathematical formulas. Then we're given planned, fixed experiments to see how those models work. Now we're prepared to use the scientific method for real-world applications, right? But wait, if you're going to work in these fields, you need more training. Grad school. I have to interrupt here with a quote from Steven Pinker. Members of our species do mad deeds, like taking vows of celibacy, living for their music, selling their blood for movie tickets, and going to graduate school. Okay, now the faculty provides deeper understanding of the theories in more lectures. Then they offer you choices of research areas, historical literature references, and lab space to start your experiments. As a result, you get a degree, and as a proven professional experimentalist, you become a member of industry or academia. You start with an intriguing problem to solve. You choose the most likely significant variables or factors to examine based on theory, literature, experience, including from your team, and your expert intuition. You evaluate each of these factors while holding other factors constant to keep the experiments manageable. Your results produce a predictive model which you verify and publish in reputable journals or add to a company's proprietary information. You might get the opportunity to buy tickets to Stockholm. What could possibly go wrong? What can and often does go wrong? Your model stops working? You can't get the right results by changing A, B, and C? You find a new variable that helps, but only sometimes. Somebody else gets better results, but their model is quite different. You can't scale it up to higher volumes or in different places. Was the source of a material the problem? Your model was wrong or incomplete. So how do you find causation using experimental methods? First of all, you need to discover what factors actually affect your observations. Further, you need to know if those factors are independent. If not, then which factors depend on each other? From those significant factors, you can construct an equation that predicts the results you find. What is the most efficient method to find that equation that takes the least time and resources? Often, it's also important to know what factors affect the variability in your results. This is especially important in industry. This search for causation is the only way to produce control and predictability. Let's use the most common method to investigate three possible variables, A, B, and C. Notice that I'm using the terms variable and factor as the same thing. You have low values and high values for A, B, and C. You can evaluate each factor one at a time while holding all the other factors constant. Let's increase factor A while leaving B and C constant to see if A is significant. Then do the same for B and C. You don't need to repeat A, B, and C all low in the B and C trials. With 4 duplications of each setting for standard statistical validity, the total number of runs is only 16. Did we get causation from those 3-factor, one-at-a-time experiments? We probably found out if any of those factors had independent effects. Check. Any information about dependencies between A and B and C? No. Do we have a predictive equation for this process? No. Do we know which factors affect variability? No. Was 16 runs the most efficient set of trials? Don't know. Let's try something else. Maybe instead of one at a time, we can change all the variables we can think of at the same time. Here's a real example of a complex pre-production experiment. Instead of looking at one variable at a time, 8 variables were changed during only 5 separate experiments at several different levels. This is worse than one at a time. This is not atypical of what can be found in industry and academia. This team was highly educated and experienced. Is it possible to design an efficient experiment that would determine all the effects of all these variables and have a truly predictable production process? The answer is yes, and the method is over 100 years old now. Finally, here's the punchline. The most powerful experimental tool, statistically designed experiments, were developed by the father of statistics, Sir Ronald A. Fisher, in 1923. He also developed analysis of variance, inference testing, maximum likelihood estimation, population genetics, and much more. But currently, out of 5,999 colleges in the U.S., only 57 actually teach design of experiments, or DOE, after 100 years now, and usually only as an option in the math department, not science or engineering. This is also typical in Europe and Asia. DOE is actually very important to high-tech companies, so they often either require it or teach it themselves. Intel, for example, even teaches DOE to technicians. Sadly, the term DOE is now often falsely attached to any planned experiment, usually out of ignorance. Real DOE is not hard to learn and use, so let's get to it. We're going to learn just one of the fundamental DOE experimental methods, called factorial DOE, that's quite different than one at a time. Let's place A, B, and C into a 3D cube. Let's also change the low and high to -1 for low and +1 for high. For example, that means that the point in the left front corner is -1, -1, -1. At the top and back of the cube is the point +1, +1, +1. Now look at the left side and right side of the cube. You see that all 4 points on the left side have A at the -1 value, and all 4 points on the right side have A at the +1 value. The effect of A is the difference between the results at the 4 left points and the results at the 4 right points. While A is being changed, B and C are being changed equally. In the same way, the effect of B is the difference between the results of the 4 bottom points and the results at the 4 top points of the cube. The effect of C is the difference between the results at the 4 front points and the results at the 4 back points of the cube. This is only a total of 8 trials. More efficient than the one at a time 16 trials, yet statistically valid. Fisher emphasized 3 essential properties: balance, replication, and randomization. Let's put our 8 points into the Hadamard matrix table. The 8 points are now the runs in the first column. We put each factor into the columns A, B, and C with its low and high settings. You see that there are 4 -1 and +1 settings balanced in each factor column, but they are arranged so that all 8 settings of A, B, and C are the 8 unique points of the cube. This is a set for each factor. Balance is essential for the experiment to be statistically valid. Let's bake some brownies and find out what factors give us the best taste. We'll compare 2 brands, 2 amounts of sugar, and the number of eggs. Of course, when you put the actual amounts in the table, you have a recipe for each run. I get to be the taster. Now we compare the +1 and -1 settings for factor A. We just do a simple average of the low and high A results and find that A affects the results strongly all by itself. 14.5 to 10. The more expensive brand tastes better. The effects of B and C are calculated the same way. These simple averages include a replication of 4 runs versus 4 runs without having to repeat any of the runs. Notice that the runs were actually performed in a randomized order on the left here. Randomization is the third essential for any experiment. Running the experiments in the original matrix order may seem easier, but opens the possibility of some other variable affecting the result. An example mistake would be to run some of the runs on one day and the rest another day. Days would become another variable in a different matrix. In the same way, we do a simple average of the low B and high B results and find that B has a much smaller effect. This method of comparing two data sets is called analysis of variance, or ANOVA. And once again, we compare the averages of the high C and low C and find no effect of the number of eggs. Remember the history of the gas law? There were 4 dependent factors. If you put 2 rabbits in a cage together, will you get baby bunnies? That depends on the sex of the rabbits, doesn't it? In a DOE, the dependency between factors is automatically discovered without the need for more trials. Looking at just the A and B columns of the matrix, the logic levels, -1 and +1, can be multiplied to produce another column representing the dependency values of A and B. Now, the average of the two products of A minus B minus is 13.5. The average of A plus B minus is also 13.5. The average of A plus B plus is the best, and the average of A minus B plus is quite small. What's going on? Let's compare these averages graphically. There is the A minus pair on the left and the A plus pair on the right, with respect to the average taste values on the y-axis. If you look at the B minus and B plus pairs on the bottom and top, you now see that taste depends on both A and B. Notice that if the two lines were parallel, there is no dependency. Dependent variables are pretty common in real life, and you get that information with DOE at no extra effort or cost. Now, the 172 years to find the multiple dependencies in the gas law could have been saved with DOE back then. If you could travel back in time, you could be the most famous scientist ever. Now we have a predictive equation for the better tasting brownies. The mean value of all the brownie runs was a 12.63 taste quality. If we choose the independent brand value of +1, more expensive, then we have the addition of 1.88 taste. The A and B are dependent, so we can choose A plus B plus for another addition of 1.88 for a total of 16.39. More expensive and maximum taste. Or we can choose A minus B minus, which subtracts 1.88 for A minus, but adds another 1.88 for A minus B minus to a taste of 12.63. That's 20% cheaper, but 13% less tasty. The options of A plus B minus or A minus B plus are not as attractive. Lower cost for a somewhat lower quality is a common choice. Knowing about this A-B dependency is often critical, yet it is free information. Here are all of the potential dependent variables: AB, AC, BC, and even a potential ABC three-way dependence with no extra runs. I am skipping the additional calculations here for the other dependencies because it's time to lean on a statistical analysis of the data. In the real world, the next step is to let the data decide which factors should be included in the model equation. Let's look closer at the statistics DOE is built on. A model equation includes the mean of all the runs, only the significant factor effects, and of course experimental error. This equation could be linear, exponential, or many other possibilities. So let's use analysis of variance to find our significant factors. Not all data is normally distributed, but this Brownie data does have a normal fit. Any significantly important factor would be expected to have a stronger effect than the normal distribution. Here's the plot of effects versus normal probabilities. The most significant factors would have strong effects and not be on the normal distribution line. We see that A and AB dependence are significant factors, with p-test values much less than 0.05. Any number of properties can be measured on each sample with no extra trials. We can also measure how chewy, how dense, or how moist the brownies are at the end of these 8 runs. You can even use this matrix to examine additional results years later if you save the data. Well, don't save the brownies. It's usually better to have a process that has a large and stable working area rather than a slippery slope, as shown here. Knowing the variance of your significant factors becomes really important if you need stability and reproducibility. I will be showing how to produce this kind of data next. All measurements have variance. Another advantage of DOE is the evaluation of the amount of variability for each factor in the experiment. Running 3 sets of each of the 8 trials, randomly of course, will produce the data that can be used to calculate variance, sigma squared, as a result. That will determine which factors have the most variance in your system. Production quality is a result of knowing where your process variation is coming from. Most DOEs are efficient fractional factorials rather than the full factorials shown so far. Here's a reduction of 32 runs and a full factorial to only 8 runs with 5 factors. What is the price to be paid for this reduction in trials? Just how far can we reduce the number of runs with more and more factors? I will give an extreme example shortly, but as I mentioned, DOE has been around for more than 100 years, so there's been a lot of work on developing very efficient DOE designs. DOE was used in munition manufacturing in World War II and the development of silicon semiconductors in the 1950s, for example. The matrices shown here are the most efficient of several possible arrangements as worked out in the 1930s. Software does it for us now. Balance, replication, and randomization is still key. Here's how we take our full factorial 8-run DOE and cut it down to 4 runs. By selecting 4 of the 8 runs that have balanced levels for A, B, and C. There is obviously another half that is also balanced. But wait! The C and AB columns are identical. Same with the B and AC columns, and the A and BC columns. The single and two-way interaction factors are aliased. Just like people with 2 names are said to have aliases, how do you know which is right? It's more likely that you have a significant result for A than the BC interaction. But you don't know for sure since 2-way interactions are fairly common. 3-way interactions are very rare. Fortunately, there are ways to determine which is the correct effect in the next experiment. This table gives a quick idea of the potential number of runs for each number of factors in fractional designs. Take some time to look at the details. The white are the full factorials. The Roman numerals in the boxes represent the aliasing. The green are the least aliased, the yellow are medium, and the red are the most aliased. The simple way to see it is to use the fingers on your hand. For resolution 4 aliasing, represented by Roman numeral 4, hold up 4 fingers, and you get 1 versus 3 or 2 versus 2 fingers. This represents the aliasing of single factor versus three-way interaction and two-way interactions. The horizontal black circle groups are examples where 16 runs can include 6, 7, or even 8 factors with the same aliasing. 21 factors can be possible with only 64 runs. Even more efficient experimental designs have been developed, as I will present next. Again, after 100 years, scientists have extensively developed statistically designed experimentation. Here's the real example I mentioned earlier. In the cockpit of smaller or older airplanes, there's an attitude gauge that can tell the pilot where the horizon is, even in thick clouds or darkness. When the plane banked and then leveled out, these gauges were sticking, and that was dangerous. An emergency group of technicians, engineers, and even VPs were assembled to find the problem. The group identified 23 variables that could cause the problem, but there was a lot of debate. I designed a single DOE of 23 variables and only 24 runs, which was completed quickly. You can imagine the high aliasing in that matrix. It turned out that a technician's suggestion of testing the gauge at the high altitude temperature of minus 50 C rather than room temperature was the solution. They changed the test, and 100% gauge reliability was the result. So now we can look at the bigger experimental picture. For example, why did we choose only 2 levels for each factor? Let's say we choose temperature values of 120 C and 140 C. But should we add 130 C? Because reality might be curved between 120 C and 140 C? Well, using 3 levels instead of 2 increases the trials from 8 to 27. Most real systems are often linear within reasonable limits, so there's a better way to check for curvature. Let's take our 8-trial cube experiment and just add a center point. No, make it 3 center points just to be sure. Now we have 11 runs, not 27, and the statistics will show us if there was curvature in the data. DOE is really an experimental discipline. Here's an example. In the first experimental space, we learned about significant factors, and there was a significant improvement. The best result was the top right back point of the cube. Now we see if it continues that way by a second experiment in the same direction. Even better. But center points discovered curvature. That suggests a maximum might have been found. Now we know where the best space has our best results. Time to use a more detailed DOE and zoom in. Taking the best result from the first 2 experiments, we zoom into the detailed 3D space surrounding it in multiple levels. A response surface method, RSM, design offers 5 levels for each factor. The 5 levels of factor A are shown in green, including one of the center points. For 3 factors at 5 levels, plus center points for each factor, adds up to only 17 trials. Again, this is only a focus for an already determined best result, from a previous fractional factorial. A detailed surface plot and a mathematical model for accurate predictions is ready for confirmation tests. The predicted confirmation points fit on the plane in this real published result. Here's another DOE technique: mixtures. Mixture components usually add up to 100%. Since there are many ways to get to 100%, you can't use a factorial design. Relative proportions are the point. Here's the example of lemonade. 3 components: water, sugar, and lemon juice can be represented by a triangle. The amounts of each have to be reduced from 100% to be drinkable. A set of experimental points can be chosen statistically with software and a best flavor determined. This works. So why bother to learn DOE for experimentation? You will find the direct effect of independent variables, find dependencies between variables, many data results can be added without more runs, generate statistically valid predictive models that can be confirmed, missing factors are predicted from the ANOVA data, factors that are the source of variability are determined, directions for next experiments are suggested, there's a wide range of custom techniques for special cases, DOE is statistically valid, supported with software, DOE experience is even expected in many science and engineering environments. Oh, and by the way, AI provides none of these advantages. DOE is about causation, not correlation, and it's been the power tool for experimentation for more than 100 years. How do you get started with DOE? There are many YouTube and online videos and full classes. But as I mentioned earlier, the terms DOE and designed experiments are often used to describe non-statistical methods. 2 classic books on real DOE are Design and Analysis of Experiments by Montgomery and Statistics for Experimenters by Box, Hunter, and Hunter. For personal computer software for designing and analyzing DOEs, there is StatEase 360, which is comprehensive, well-supported, and easy to use, and Jump Statistical, which is one part of a complex statistical platform. Welcome to the 21st century.